Welcome everyone to section 3.2. We're going to be talking about trigonometric integrals. Probably a very lovely topic for many of you. Lots of trigonometry. Okay, I know I say this all the time, but there's no real new calculus here. There's nothing new here. The struggle is all the old stuff, okay? Do you remember trig? Do you remember trig identities? Can you use trig identities? Do you remember u substitutions, integration by parts? That's basically it, okay? So it's practice putting all of these together, and we'll put some of these together in kind of new ways. Maybe kind of new, maybe something a little bit new. Okay, and this is really kind of a baby section. This is like a precursor section, a warm-up section, if you will. Nothing in this section's particularly, this is not something you should announce to your students, but nothing in this section is particularly interesting, okay? But it leads directly into 3.3. 3.3 is going to be trig substitutions, which is so useful, okay? Extremely useful. So many integrals we've seen in this class, we couldn't do because we didn't know how to do trig subs yet. So this is like an introduction, a lead-in to 3.3, which is actually interesting and actually useful. The 3.2 is useful by itself too. So it's really useful in like it's really useful in polar coordinates. So like if you remember this, where instead of an x and a y coordinate, we have a radius and an angle, an r and a theta. So it looks like this. It's useful in cylindrical coordinates, which are kind of a hybrid of polar and Cartesian, where it's like polar coordinates on the xy plane, but then you have a z value as well, cylindrical because, you know, it kind of looks like a cylinder, and then spherical coordinates, which are like the three-dimensional version of polar coordinates. You know, these all use sines and cosines, and if we're integrating in these coordinates, which we're not going to do in this class, but we could, right? If we wanted to find the area under these curves with polar coordinates and stuff like that, we'd have a lot of sines and cosines running around, okay? But don't worry, we're not doing that. Why do I have two polar coordinates images over here? And then, so that's one of the places it's interesting. Hold on, this is distracting. Another place where this material is useful is just in higher level applications of math. So specifically like signal processing. I wrote it down somewhere. I thought I wrote it down somewhere. But yeah, like signal processing, Fourier series or something really, really big. Weird. I don't know. Oh yeah, and quantum mechanics. Apparently I'm supposed to be talking about that in the third video. That's why I didn't write it down for my notes for this one. But yeah, that's some of the places where this stuff is interesting. Okay, so that's the introduction. That's why we're doing this. That's where we're at. How do we do it? So I'm already going to a new page because I want you to make some space in your notes. You don't need to go to a new page, but I'm going to go to a new page. And we're just going to we're going to make a big table. Okay? And this table is going to have a method. There's going to be 4. 1, 2, 3, 4. Leave it like one line between each method. We're going to have some methods. We're going to have specific cases that we use that method. And then we're going to have some examples. And yeah, we're going to fill these in as we go through all these videos. So we're not covering all of these today, or well, depends on when you watch them. We're not covering all of these in this first video, but I want you to have it all in one place. So as we introduce a method, we'll fill in the table. All right, sound good? Okay then. So let's do an example. Again, we haven't filled in anything in the table yet, but let's do an example. Something that you've already seen before. Example 1, integrate. Part A is going to be the integral of cosine cubed of x times sine of x dx. So this is a problem that you've already done. This has probably been on a quiz or a midterm or something. You know how to do this. And that's our first method. So our first method is just, well, how have we done this before? So in this case, well, we have two things multiplied by each other. Oh, when two things are multiplied by each other, a lot of times you use integration by parts. Trig is not super nice with integration by parts. Sometimes it works. If we had like x cosine of x, that would be really nice. But here we're going to kind of go in a circle if we use integration by parts. And it might help. It might actually work. But it's unnecessarily complicated, even if it does work. And I don't know if it'll work, but something to think about. U substitutions are also another thing that we want to think about because we have this sine x on the outside. And sine is the derivative of cosine. So we have a function inside of a function, and specifically, we have some kind of derivative off to the side. Those are the things that we look at for u substitutions. And in fact, that is our first method, u sub. Okay. I'll fill in a case well, we can fill in an example right now, I guess, right? We literally are just doing it right now. Cosine cubed of x, sine of x, dx is one example where we use a u substitution. We'll do the problem and then I'll talk about what the general case looks like. So let u be cosine of x. We choose that sort of u because two reasons. One, it's a function inside of a function. And two, because its derivative is sitting out on the outside. So du is negative sine of x dx, which we almost have. We just need a negative here and a negative here. Again, technically we want the negative here, but if I put that there, it looks like subtraction. So I'm going to put the negative in front. And now all of this is just du. So that gives us negative integral. The blue stuff is du. What's left? Cosine cubed. Cosine cubed is u cubed. I have a lot of space here. But now this integral is no problem. Just use the power rule. Add an exponent, divide by that exponent, plus c. And what is u? U is cosine. That's our final answer. We can check our final answer by taking the derivative and hoping that when we take the derivative, we get our original integrand. That's it. That's the first video, sort of. Half of the first video. So we use this whenever we have the integral of sine to some exponent of x times cosine of x dx. Or you can switch the cosine and the sine here. And in fact, because I don't want to write all of these twice, you can always switch any sine or cosine in this table. So I could write a second formula that said sine of x times cosine to the j, but I don't want to. It's just clutter. But if you want to write another case under each of these where you put the j on the other one, you can do that. All right, and this is an example where j is 3. Let's do another problem. And then that'll be a new method. All right, part B is going to be the integral of cosine squared of x, sine cubed of x. And again, every time you see an integral of two things multiplied by each other, I want you to think of u substitutions. Integration by parts with a u and a dv. The problem is that neither one of these are really easy to integrate. So integration by parts is not going to be very common in this section, but that's one of the big things to look for integration by parts, is if you have two things multiplied by each other. So don't forget that, even though we're not using it a lot in this section. We can think of a u substitution, which might work. There might be a u substitution you can do off the top of right off the bat. I don't see it. And the reason why it's hard is we don't have a derivative sitting out here. Now you could rewrite this. I wouldn't write this down what I'm about to do. But you could rewrite this, right, as sine cubed of x times cosine of x times cosine of x dx, right? And then if u is sine cubed, this is our du. But the problem with that is we still have this guy hanging around. So a u substitution is not really going to be helpful here. we're going to use a Pythagorean identity. So this identity sheet will be your best friend. It doesn't have to be this one. Any trig identity sheet that you have, I would highly recommend putting in your notes. And this just has a bunch of different identities. Pythagorean identities are going to be a big one. And these ones you should be pretty familiar with already, even without an identity sheet. The first one, I'm hoping you have memorized already. And the second two are just the first equation when you divide by sine squared or cosine squared of u. Okay? So sine squared plus cosine squared equals 1. So you might say, and I hope you think about this. I hope this is what you think. It's wrong. It's not wrong. It's just not helpful. But I hope you see, oh, we can put everything in terms of sine squared. So don't write this down. But if we do that, right, cosine squared is 1 minus sine squared. So this is actually not helpful, but I want you to think about it. Because look what it gives us. It does get everything in sine, which is good. But we can't do these integrals. Actually, it turns out later on, I'll tell you how to do these integrals. But right now, we haven't talked specifically about doing them. It doesn't make things any nicer. Let's use the Pythagorean identity on the other one. Okay. But Jason, there's no Pythagorean identity for sine cubed. You're right. What if we write it as sine squared of x times sine of x dx? Now what's going to happen? We use the Pythagorean identity on this guy, and then this becomes only cosines, and we have the derivative of cosine right here. That's going to be our second method. Okay? Second method is going to be using Pythagorean identity. Which turns into a u sub. So an example is the problem that we are doing right now. Cosine squared of x, sine cubed of x, dx. And just like before, I'll fill in the general case after we do this problem. Oops. Okay, so let's use the Pythagorean identity and see what we get. Sine squared is 1 minus cosine squared. Solve that sine squared of x dx. And now we can do a u substitution. You do the substitution now or later. I think I like doing it now because it just makes the simplifying step a lot easier. If u is cosine of x, which is a good choice of u because there's a lot that we're doing with cosines, then du is negative sine of x dx. So we just add a negative, compensate with the negative. Now all of this blue stuff is just du, and we're left with negative. The blue stuff is du. Cosine squared is u squared. 1 minus cosine squared is 1 minus u squared. And now it's easier to simplify. We distribute the u squared. It's not that much easier to simplify, but it's a little easier to simplify. And we can evaluate. This becomes the integral of u squared minus u to the fourth when we distribute. And now we just use the power rule, and we're good to go. So that's going to be negative u squared is u cubed over 3. U to the fourth becomes u to the 1/5 u to the 5th, right? Just like so. Plus c, and there's a negative in front of all of it. So that's going to be negative 1/3. U is cosine. We're distributing that negative. Cosine to the 5th. And again, technically the plus c is inside and gets the negative, but it's still a constant, so this is very common. And this is our answer. Check our answer by taking the derivative and then using the Pythagorean identity afterwards. All right. Let me know if you have any questions. That's it for this video. Oh, no, it's not. So what's the general case that we do this with? All right. It's going to be the integral of sine to some power and then cosine to an odd power. I'm going to write that as 2k plus 1. That odd power is important because we need a leftover. The even part gets Pythagorean identitied, and the leftover is for that du. And again, remember, you can write two formulas. One, you can switch the exponents. And in fact, right, that's what would happen here. This is the one where the odd is on the sine instead of the odd is on the cosine, but it doesn't matter. I'm only using one. But yeah, these can switch. And all of that holds. That's what this comment in red means. I'm just not going to write these cases twice. But yeah, sines and cosines are essentially the same because of the Pythagorean identity. So anytime you have some exponent and then an odd one, and you can notice, by the way, that this first case is just a subset of the second case, where k is equal to 0. You can use Pythagorean identity like this. All right? Let me know if you have any questions. That is the actual end of the video, and good luck.